Our last chapter, chapter 19, is on radioactivity and nuclear chemistry. So this topic is going to be quite different from everything else we've looked at. We've been talking about electrons, transferring electrons, that kind of chemistry. Nuclear chemistry involves the nucleus, obviously. That's why it's called nuclear. And we're going to be back talking about protons and neutrons. So what is radioactivity? It's the release of tiny high-energy particles or gamma rays from an atom. And those particles are ejected from the nucleus. Radioactivity was discovered by Becquerel. He noticed that certain minerals were constantly producing energy that could penetrate matter. And he looked further into them and determined that all of them contained the element uranium, and that these rays were produced even though the material was not exposed to outside energy. So it wasn't like it was absorbing energy and then releasing energy like we talked about with light and electrons. He originally called them uranic rays because they're from uranium. They seem to be like X-rays, but not related to phosphorescence. And the big question that this brought up was there was energy being produced without an energy input. And we know from our study of thermodynamics that energy needs to come from somewhere. So the question is, where is this energy coming from? Now we can talk about Marie Curie. I'm sure you've heard of her, very famous scientist. She broke down these minerals containing uranium, used an electroscope to detect where they were coming from, and she discovered they were emitted from specific elements, uranium being one of them, but she also discovered new elements. Radium was named for its green phosphorescence. Polonium she named for her homeland. She was Polish. And because these rays were no longer just from uranium, but from other elements as well, it was renamed radioactivity. So here you can see the phosphorescent radium on a watch dial. More research was done, and Rutherford, who studied the atom in great detail, discovered that there are 3 types of rays. Alpha rays have a charge of +2 and a mass of 4. We now know that that is a helium nucleus. There are beta rays, which have a charge of -1 and a negligible mass. They are electron-like, but again, they're coming from the nucleus. And gamma rays, which are a form of light energy. They're not a particle like alpha or beta waves. In addition to alpha, beta, and gamma, some nuclei will emit positrons, which are like a positively charged electron. And some will undergo electron capture, where a low energy electron is pulled into the nucleus. Radioactivity comes from these elements that are spontaneously decomposing into smaller nuclei. It's called radioactive decay. Those nuclei that undergo radioactive decay are unstable, and in order to decompose, the nuclide emits a particle or energy. More terms for you. The parent nuclei is the nucleus that's undergoing radioactive decay, and the daughter nuclide is the new nucleus that's made. So that should make some sense. And if you look at your periodic table, all nuclides with 84 or more protons are radioactive. They are unstable. Here are some atomic symbols you should be familiar with. The first 3 we've talked about before. Protons, you can use a P+. If you want to write the nuclear symbol, It's 1,1H, so a mass of 1, a charge of 1, and then that's a hydrogen, or you can use the P for proton. A neutron doesn't have a charge, so there's the 0 there and a mass of 1. An electron doesn't have any mass, or has negligible mass, and a charge of -1. An alpha particle has a mass of 4 and a charge of 2. You can either use alpha or helium. A beta charge is like an electron, and then a positron is like a positively charged electron. In this radioactive process, elements are changed from one element to another element. So if you think way back to Dalton's atomic theory, one of them was that elements don't transmutate. It's true for chemical reactions, but not for nuclear reactions. And remember, what defines an element is the number of protons. So in order to change one element into another, you need to change the number of protons in the nucleus. So this figure here is showing radioactive decay, alpha decay, and that changes the number of protons in the nucleus. So we get a new element when an radioactive element undergoes alpha decay. I had briefly talked about this already. Chemical reactions, which is what we've studied so far, involve changes in the electronic structure of the atom, so we're shifting electrons around. Nuclear reactions, on the other hand, are going to involve changes in the structure of the nucleus. We can describe nuclear processes with nuclear equations. We're going to use the symbol of the nuclide to represent the nucleus, and then we'll want to conserve atomic numbers. Just a reminder, the atomic number goes on the bottom, and then the mass number goes on the top. They need to add up to the same number on both sides. So just like you've been balancing chemical reactions with regards to element and charge, we're going to balance nuclear reactions. We're just going to balance the atomic number and the mass number. Here's a picture of alpha decay. You'll want to memorize that an alpha particle is a helium nucleus, has a mass of 4 and an atomic number of 2. Beta decay is a beta particle, which is like an electron. It's emitted from the nucleus. And what actually happens is a neutron loses kind of the negative part of itself and becomes a proton. So we can go from a radioactive carbon nucleus, carbon-14, change one of our neutrons into a proton. So we've added 1 to our atomic number. Our mass number stays the same because our beta particle doesn't have any mass associated with it, and it becomes a nitrogen. Gamma is a high energy photon of light. It does not change the nucleus itself, no loss of particles. It is the least ionizing but the most penetrating. And it's going to generally occur after the nucleus undergoes some other kind of decay and the remainder of the nucleus is rearranging. A positron, again, we are changing the nucleus. In this case, we're having a proton lose the positive part and become a neutron. So we don't have a change in mass, but we do have a change in atomic number. So we can go from a carbon-10 radioactive nucleus to a boron nucleus. Electron capture is our last kind of radioactive decay. It occurs when an inner orbital electron is pulled into the nucleus. the net change is going to be the same as a positron emission, but we're not emitting a particle. And so a proton and an electron will combine to make a neutron. So your mass number is going to stay the same, your atomic number will decrease. So we can have some particle changes here. This is just a summary. Beta emission is a neutron changing into a proton. Positron emission is a proton changing into a neutron. And electron capture is a proton changing into a neutron. Here is a summary table for you, table 19.1. So you'll want to review that and make sure you're familiar with all these kinds of radioactive decay. Here is a sample. Write the nuclear equation for positron emission from potassium-40. So the first thing you'll want to do is be able to write the nucleide symbols for the starting radionucleotide and the particle. So potassium-40, the 40 is the mass number. Potassium is element number 19. So you're going to have the mass, 40, and the atomic number, 19. And then a positron is the 0 plus 1 electron. So we can set up the equation. We are taking our potassium, 40. We are ejecting a positron, and then we're going to become some other element. Now, the mass numbers and atomic numbers need to add up to the same thing on both sides. So our mass number, since this is a 0, is still going to be 40. Our atomic number, though, 1 plus what is 19? The answer is 18. And then you have to go to your periodic table and see what is element number 18. And the answer is argon. So the atomic number determines what your symbol is. So there's the answer. So here's some practice. I would recommend pausing, and then you can check your answers. Write a nuclear equation for each of the following. Alpha emission from uranium-238. So uranium-238 is going to be 238 on the top. Symbol for uranium is a U. Uranium is element number 92. And we are emitting an alpha particle, which is a 4-2 helium nucleus. Then 238 minus 4 is 234. And 92 minus 2 is 90. And element number 90 is thorium. All right, beta emission from neon-24. So 24, neon is number 10. We're emitting a beta particle, which is a 0 minus 1e. It's electron-like. And so then our mass number does not change. Our atomic number is going to go up by 1. So we're going to end up with an 11. And element number 11 is sodium. Positron emission from nitrogen-13. So 13,7 nitrogen. We are emitting a positron, which is like a positive electron. And then our mass number did not change. Our atomic number is going to be a 6 now. 6 plus 1 is 7. And element number 6 is carbon. And electron capture by beryllium-7. So 7, beryllium is element number 4. And then Be plus an electron, because we're doing electron capture. Our element number does not change, but our proton becomes a neutron, and so we're left with 3 protons, and element number 3 is lithium.